inequality, we're going to give a whole range of answers. So if I'm looking to solve this inequality of y divided by 3 is greater than or equal to 4, I want to do the opposite of what's happening to y. This is a one-step equation because there's only one operation happening. So I'm multiplying by 3, multiplying by 3. So now I have y is greater than or equal to 12, which means y could be 12, or it could be any number larger than 12, and that's why we graph our answers. Because if I know it could be 12, because 12 is equal to 12, I then have to understand that it could also be numbers bigger than 12, would make it true. If I try a number smaller than 12 for y, if I say 11 is greater than or equal to 12, well, that's an untrue inequality, so that does not work. So when I'm going to graph it, I'm going to put 12 somewhere in the middle. I'm going to count up a few and count down a few. And then I have to decide if I'm using an open dot or a closed dot. Whenever it's or equal to, I want to use that closed dot. Because 12, kind of like multiple choice answer, you bubble in your answer. 12 is a possible answer here. 12 works. And then I'm going to point towards the other numbers that are also possible answers. So 13 works, 14 works, 15 works. 16, 17, 18, 100 would work, 200 would work. Any number that was bigger than or equal to 12 would work. Sometimes you'll see these little brackets and you'll have a possible solution set. So you could say that 12, 14, and 16 were possible solutions because each one of those numbers is included in this range. Here's a two-step inequality. It says a divided by 2 plus 4 is less than 7. So I still want to use my railroad tracks because I have to make sure what I'm doing here, I'm also doing here. Because this is a two-step equation, I want to get rid of my addition first. I would do that by subtracting 4, which just cancels it out on the left side, and then I do 7 minus 4, which would be 3. I bring down the symbol, and I bring down what's left, which is a divided by 2. Then to get rid of a divided by 2, I'm going to multiply by 2. 3 times 2 would be 6. My less than sign, and a. So I can always then do some testing. If I say 5 is less than 6, does that work as a true inequality? It does. If I say 6 is less than 6, that does not work because 6 is equal to 6. It's not smaller than 6, so that won't work. And if I go 1 up from 6 as 7 is less than 6, that does not work. I'm still going to put 6 somewhere in the middle because that's my starting point. I have to decide an open dot or a closed dot. And I only want to use an open dot if when I plug in the number itself, it's a true inequality. So here I plugged in 12, it was true, so I colored in the dot. Here it's not or equal to, it's only less than. So I have to leave an open dot because 6 does not work as part of the solution. Now I want to point towards the numbers that make it true. So 7 was not true, 5 was true. So I'm going to draw my arrow pointing towards 5 and all of the numbers smaller than 6. Once again, if I wanted to look at a solution set, you might see these brackets, and you could see something like 3, 4, 5, and then you could see 7, 8, 9. And if these are my two solution sets, which one would be true? This one. All of these would be true values for A. These would not make the inequality true. Equations. This one is one of those situations where I might want to use the commutative property to rewrite it. So I can rewrite it as 2b plus 4 is greater than 18. And now I want to eliminate what's happening to b. So first I'm going to eliminate the plus 4. And I'm going to eliminate that by subtracting 4. So now I have 2b is greater than 14. And now I'm going to divide by 2 to get rid of multiplied by 2. So divide by 2, divide by 2, and I'm going to be left with b is greater than 7. So now I need to graph my solution. So I'm going to put 7 somewhere in the middle, and I'm going to count up a few and count down a few. I have to decide open dot or closed dot. If I plug in 7 and write 7 is greater than 7, that's untrue. So I want to leave an open dot, because that means 7 is not a possible solution. I would just try one up and one down. So is 6 greater than 7? No. Is 8 greater than 7? Yes. So I want to point past 8 towards all of the numbers that would make this inequality true. Last example here has those parentheses. So just like with equations, we want to use that distributive property. And I want to do 3 times 2a. And I want to do 3 times 3, which is going to give me 6a plus 9 is greater than 39. So now I would be ready to solve it. I'm just going to rewrite it up here because I don't want to run out of space. So I'm just rewriting my inequality. 6a plus 9 is greater than 39. And I want to get rid of that plus 9 first by subtracting 9. Subtracting 9, and that's going to be 30 greater than and 6a. And now to get rid of 6a, I'm going to divide by 6, because when a number is attached to the variable, it's being multiplied. So I'm going to do divide by 6, divide by 6, and I'm left with a is greater than 5. And now to graph that, I'm going to put 5 somewhere in the middle here, count up a few, and count down a few. So 6, 7, 8, 9, 4, 3, 2, 1. I have to decide open dot or closed dot. If I say 5 is greater than 5, that's not true, which means I can't include 5 as a possible answer. So I'm going to leave the dot open. Then I can try one up and one down. So 4 is greater than 5. That's also untrue. That does not work. If I say 6 is greater than 5, that does work. So I'm going to point towards the right, towards 6, and all of the other numbers that are greater than 5. So Solving inequalities, same steps we followed when we were solving equations, except now we actually have to graph our answer on the number line. So when we are doing these solutions, please remember we're going to use the distributive property to eliminate parentheses if needed. We're going to use inverse operations to get rid of any addition or subtraction. We're going to use inverse operations to then eliminate any multiplication or division. And then we're graphing the solution set. So this step is the extra step from equations. When it's a less than or greater than sign, we use an open dot. If it's a less than or equal to or a greater than or equal to, we use the closed dot. And then we want to point towards the numbers that make that inequality true.